Everyone knows this, right? If a tree falls in a forest and no one is around to hear it, it still makes a sound. Reality doesn't depend on us. The universe doesn't care whether we're watching or not. That feels obvious, almost childish to question, but wait, here's the thing. In the quantum world, that assumption quietly breaks. Because at the smallest scales of reality, observing something doesn't just reveal what's already there. It changes what happens. And I don't mean in a poetic, your thoughts shape your reality way. I mean literally, mathematically, experimentally. Think about that for a second. How can looking at something change what it does? How could reality behave one way when unobserved, and another way the moment we try to measure it? We're used to the idea that measurement is passive. You check the time and the clock doesn't care. You step on a scale and your weight doesn't suddenly change because you looked at the number. So when physicists first encountered evidence that observation itself alters physical outcomes, they didn't panic. They assumed something must be wrong. But experiment after experiment kept saying the same thing. You don't just uncover reality, you participate in it. Now here's where most explanations go wrong. They say things like the observer collapses the wave function, toss around jargon and move on. But that doesn't really answer the question. Why should observation matter at all? What counts as an observation? Is it consciousness? Is it a measurement? Is it interaction? And more importantly, what does this say about the nature of reality itself? Because once you accept that observation changes outcomes, you can't unsee the implications. It forces you to rethink objectivity. It forces you to rethink causality. It even forces you to rethink what it means for something to exist. So let's slow down. Let's start where everyone thinks they understand things, and then carefully walk into the place where that understanding falls apart. Because the story of quantum measurement isn't just about particles and equations. It's about the uncomfortable realization that the universe doesn't behave the way common sense says it should. And once you really see that, there's no going back. Music fades slightly. To understand how we got here, we have to rewind to a time when physics felt complete. By the late 1800s, classical physics was riding high. Newton's laws explained motion. Maxwell's equations explained light. The universe looked like a giant, perfectly predictable machine. If you knew the position and velocity of every particle, you could calculate the future forever. This idea even had a name later on, determinism, but cracks were already forming. One of the first came from a deceptively simple problem, blackbody radiation. When physicists tried to calculate how hot objects emit light, the equations predicted something absurd: infinite energy at high frequencies. That clearly wasn't happening in real life. Enter Max Planck. In 1900, he made a move so radical he didn't fully believe it himself. He assumed energy could only be emitted in discrete packets, quanta. At first, this was just a mathematical trick, but it worked. A few years later, Einstein took it seriously. He used the idea of quanta to explain the photoelectric effect, showing that light sometimes behaves like particles. And suddenly, the neat classical picture began to wobble. Then came Niels Bohr. He proposed that electrons in atoms don't orbit smoothly like planets. They jump between discrete energy levels. No explanation for why, just rules that worked. By the 1920s, quantum mechanics exploded into existence almost overnight. Heisenberg developed matrix mechanics. Schrödinger introduced wave mechanics, and here's where things got weird. Schrödinger's equation didn't describe particles as tiny billiard balls. It described a wave of possibilities, not the electron is here. But the electron might be here or here or here. Physicists called this the wave function. It didn't tell you what is. It told you what could be, and as long as you didn't measure anything, the wave function evolved smoothly, predictably. But the moment you performed a measurement, everything changed. Instead of many possibilities, you got one actual outcome. The wave function collapsed, but collapse wasn't part of the equation. It wasn't derived from the math. It was added by hand. This bothered people a lot. Einstein famously hated it. God does not play dice, he said. He believed reality had definite properties whether we looked or not. Quantum mechanics as it stood seemed incomplete, and this tension came to a head in one of the most famous thought experiments ever proposed. In 1935, Einstein, Podolsky, and Rosen introduced what we now call the EPR paradox. They imagined two particles created together, then separated by a large distance. Quantum mechanics said their properties would be entangled. Measure one and you instantly know something about the other, no matter how far apart they are. Here's what you'd expect. Information shouldn't travel faster than light, but that's not what happens. Experiments later confirmed it. The correlations are real. They can't be explained by hidden instructions carried from the start. Something about measurement itself was fundamentally non-classical. And at this point, physics had crossed a line it could never uncross. Now let's do the experiment that really forces this issue into the open. Imagine firing electrons one at a time at a barrier with two slits in it. Behind the barrier is a screen. If electrons were just particles, you'd expect two piles behind the slits. But that's not what happens. Over time, a wave interference pattern appears. Bright bands, dark bands. Each electron behaves as if it went through both slits at once. Here's the thing, this happens even if you send electrons one at a time. No interaction, no crowd effects. Now here's what you'd expect next. If you place a detector at the slits to see which slit the electron goes through, you'd still get the same interference pattern. But that's not what happens. The moment you observe which path the electron takes, the interference disappears. You get two simple piles. The act of measurement changes the outcome, not after the fact. At the most fundamental level, think about it. The electron doesn't gradually lose its wave nature. It doesn't partially interfere. It's all or nothing, and it doesn't matter how gentle the measurement is. Even the possibility of knowing which path destroys the interference. Now pause. What exactly caused the change? Was it the detector physically disturbing the electron? Physicists checked. They designed experiments where disturbance was minimized beyond any classical explanation. Still gone. So the explanation couldn't just be measurement bumps the particle. Something deeper was happening. This is where Heisenberg's uncertainty principle often gets misunderstood. It's not just about technological limitations. It's not saying we're bad at measuring. It's saying certain properties don't have definite values simultaneously. Position and momentum aren't hidden from us. They aren't both real at the same time until measurement forces a choice. Wait, let me say that differently. Reality doesn't come pre-packaged with all properties defined. Some things only become real when measured. Now here's where it gets strange in a beautiful way. Take Schrödinger's cat. You know the setup: a cat, a radioactive atom, a vial of poison. According to the math, until you open the box, the system is in a sewer position. Alive and dead. People often joke about this, but Schrödinger wasn't joking. He was pointing out how absurd this sounds. But the absurdity isn't the cat. It's the assumption that measurement is passive, because quantum mechanics doesn't say the cat is secretly alive or dead. It says the concept doesn't apply until measurement. Now connect this to everyday life. When you decide what to eat, the options feel real. Pizza, rice, nothing. Once you choose, the alternatives vanish. Not physically, but in relevance. quantum measurement works similarly but at the level of physical law. The universe evolves as possibilities. Measurement turns possibilities into facts. And no, this doesn't require a human mind staring at particles. That's another misconception. Observation in physics means an interaction that records information irreversibly. A detector, a photographic plate, anything that leaves a trace. But even this leads to another problem. If everything obeys quantum laws, then detectors are quantum systems too. So where does the collapse actually happen? This is the measurement problem. If the wave function evolves smoothly and everything is part of the wave function, why do we experience definite outcomes at all? Some interpretations say collapse is real. Others say it never happens. In the many worlds interpretation, the wave function never collapses. All outcomes occur in different branches. When you measure, you don't force reality to choose. You find yourself in one branch. One insight explains three things at once. Interference disappears, probabilities make sense, and no collapse is needed. 3 for 2. But whether you accept many worlds or not, the core fact remains: measurement is not neutral. And this has consequences. Quantum computing relies on this. Qubits exist in superpositions. Measurement extracts information but destroys quantum advantage. Quantum cryptography relies on it too. Eavesdropping is detectable because the measurement leaves a mark. Reality resists being watched without consequence. So what does this all mean? It means reality isn't a static stage where events unfold. It's an active process. Facts are not just there waiting, they emerge. And the deeper you look, the more it feels like information is fundamental. No matter, not energy, information. David Deutsch and others argue that the universe behaves like a computer, not a laptop, a physical process where computation and physics are inseparable. Measurement is computation. It's the extraction of information from possibility. And limits like the speed of light, uncertainty, and entropy aren't bugs. They're constraints on information flow. This changes how we think about knowledge. There are things you can't know simultaneously, not because you're limited, but because reality is. It also changes how we think about causality. Effects aren't always tied to a single, well-defined cause, and it humbles us. Because the universe doesn't arrange itself to be easily observed, observation is an intervention. Music slowly builds, so where does that leave us? We started with a simple assumption. Reality exists independently of observation, and we ended somewhere far stranger. Observation doesn't create reality out of nothing. But it shapes which version becomes real. Understanding this doesn't close the book on physics. It opens it wider. Each insight triggers more questions. Each discovery leads to deeper puzzles, like an avalanche. One small realization destabilizes everything above it, revealing layers we didn't even know were there. And that's the beauty of it. Reality isn't finished, and neither is our understanding.